Hi, it's Kristen McCann, and this is your Reaction Rates podcast. We're going to go over all the factors that affect the rate of reactions, and then we're going to give some examples of biological catalysts as well as some inorganic catalysts in your everyday life. All right, so when we talk about reaction rates, what we're talking about is how fast does a reaction proceed from your reactants to your products. And there are a number of factors that affect the rate of the reaction. First is temperature. So when you increase temperature, rate also increases. And the reason for this is twofold. First, when you increase temperature, you're increasing the kinetic energy of the molecules. So now they're starting to move more. When you increase movement, you're increasing the likelihood that there's going to be a collision between two reactants that is going to result in the formation of a product. Second, when you're increasing the energy or the movement of those molecules, they will use that energy as they're colliding to cleave bonds or to break bonds in the reactants and reform bonds with the products. So now the molecules are going to have enough energy to cause that bond breaking. The second thing that speeds up a rate of a reaction is a catalyst. Catalysts can increase the rate without using up the catalyst, and they do this by lowering the activation energy. Every reaction has a certain amount of energy that is needed or required to start the reaction. If you can lower the amount of energy needed, it's more likely you're going to be able to get to the product side of a reaction. That increases the rate of your reaction without being used up in the reaction. The last thing you can do to increase the rate of the reaction is to increase the concentration of the reactant. So your rate increases as the concentration increases. So essentially what you're doing is you're adding more of that starting material. When there's more molecules in the same space, the likelihood of collisions happening increases, and the likelihood of a collision happening and the rate orientation to result in a product also increases. A good example of a catalyst being used in our everyday life is the catalytic converters, which are in all of your vehicles. When we talk about the combustion of gasoline, it's not as simple as what we show in class. You're not going to wind up with all the gasoline being combusted, winding up with only CO2 and only water vapor as a result of it. In the 70s, the vehicles that were combusting gasoline didn't have catalytic converters, and they were leaving these byproducts of the combustion of gasoline. They were leaving some unreacted gasoline molecules. They were also producing carbon monoxide, which we know is not a great gas to have around, and they were producing nitrogen monoxide. Nitrogen monoxide is a contributing factor to acid rain. So we're really changing our environment by spitting out this unreacted gasoline, carbon monoxide, and nitrogen monoxide. So one way to bypass this problem and to make sure that all gasoline was reacted, all carbon monoxide molecules are broken down, and so are nitrogen monoxide molecules broken down, was to add a catalytic converter. So a catalytic converter has an inorganic plate. Usually this is made out of, it can be made out of palladium, platinum, or rhodium. Missed that one. So rhodium, palladium, platinum. And that surface catalyzes each of these reactions that you're seeing here. So it breaks down the unreacted gasoline into CO2 and H2O. Mind you, that's unbalanced. It breaks down the carbon monoxide into CO2, and it breaks down the nitrogen monoxide into nitrogen gas and oxygen gas. So the products of this, yes, we know CO2 is not a great thing to be pumping into the environment, but it's a lot better than that unreacted gasoline, the carbon monoxide, or the nitrogen monoxide. So this provided a way to catalyze those reactions that would have been left incomplete. So in the last example, we talked about an inorganic or a metal acting as a catalyst for reaction when we looked at rhodium, platinum, and palladium converting all that unreacted gasoline. Enzymes, however, are an example of a biological catalyst. So it's a protein that does the same job. It's catalyzing a reaction by lowering the activation energy. So on this blue line, we didn't get a chance to look at this before. This is the energy required for a reaction to proceed from the reactants to the products. What an enzyme does is it lowers the activation energy. So it takes less energy to get the reaction to happen, and more likely that you're going to wind up with a product. This enzyme that you're looking at is called lactase, and lactase is an enzyme responsible for cleaving the bond between the two monosaccharides, galactose and glucose, that form lactose. So this is lactose. The lactose enters the active site, and then the enzyme is able to use water to break this glycosidic linkage, and what it forms is a 2 monosaccharide. So this is the first step in the digestion of lactose. Individuals who are lactose intolerant don't make the lactase enzyme and therefore cannot break apart the disaccharide lactose into its monosaccharides. So they have to avoid dairy.